Hello everybody. So now I'm trying it for the third time because I discovered always still some mistakes inside. We are continuing now with the introduction to face pathology. That is the last small chapter in our mineralogy class. I sent today around this booklet which is called Mineralogical Thermodynamics, and there we will do some in class now some principles in thermodynamics and mineralogical thermodynamics, and in the practicals we will do some thermodynamic calculations. So because due to the fact that we are suffering now because of the COVID-19 virus, the university will remain to be closed till the 5th of May. So, and therefore I made in the examination in the practical examination, two blocks. Block A is for microscopic examination, or a practical microscopic examination, and block B is for some qualitative and quantitative mineralogical thermodynamical calculations, just in case if we did not find enough time towards the end of the semester to run our microscopic practicals, and therefore we are now a little bit flexible. Yeah, I will send you then also around some exercises. So now we are starting just with the very principal things in phase pathology. And therefore we are starting now with some definitions. Yeah, so we define. We have the pressure P, we have the temperature T, we have the volume V, we have the internal energy U, and we have the entropy S. So the most important variables in mineralogical thermodynamics, that is the pressure and the temperature. Most or all of the processes on Earth are pressure and temperature controlled. And if we have a temperature dependent process as well as a pressure dependent process, then we are facing then always changes in the volume as well, of course. Yeah, if you are looking for the system water, yeah, H2O, water occurs in three modifications. That is ice. That is the solid modification, yeah, and ice is a mineral. Then we have the liquid modification, that is water, and we have the gas phase, and that is then steam. So while we are increasing the temperature of water, then we are increasing the volume, yeah, of the water, and we are increasing the volume dramatically or drastically at 100 degrees Celsius, where we are forming, or where we are facing the boiling point and we are forming out of the liquid water steam. So then we have a drastic change in volume. We have the internal energy of a phase, which is U, I mean just here the shortcut U, and that depends also on pressure and the temperature. Then we have the entropy, and the entropy, that is the order or disorder of a phase, and that has the shortcut S. That has the shortcut S, and that means, for example, when we are going again to our system H2O, when we are heating up water, then the disorder of the liquid water becomes higher, yeah? And if we are coming to the boiling point, then the disorder, when we are going from liquid to the gas phase, becomes much higher. So the entropy is also strongly dependent on the temperature, like the volume. So, but the volume is then also strongly dependent on the pressure. If you are going back to your course material and if you are checking your SiO2 modification and all the other minerals, but in the system SiO2 you can observe it very nicely, then you will find out very easily on the slides which I have handed out to you that the density will increase with increasing pressure, and that is caused by the decrease of the volume of a atomic unit cell. So then we have the first thermodynamic law, which is the differential of U, and that is 0, whereas U can be described as dQ plus dW, whereas Q is the heat which we're putting into a system, and W is the work which we are putting into a system. So then we have the second thermodynamic law, that is the differential of the entropy. Then we have dQ reversible divided by the temperature T, and that is always bigger or it is 0. Bigger 0 or 0. A combination of both thermodynamic laws can be described as du is TdS minus PdV. So there we have everything inside. We have now U, that is the internal energy. We have T, that is the temperature. We have the D for the differential, and then we have S for the entropy. We have minus P, which is the pressure. We have D for the differential, and volume, and the volume, yeah? So we have all 5 variables now in this combination of the first and the second thermodynamic law. So then I have to introduce other values which are necessary for the simplification and therein for the projection of various thermodynamic systems. And these are, we have the enthalpy, which has the shortcut H and can be described by the formula or by the function U plus PV. U, the internal energy, plus P, the pressure, multiplied by V, the volume. Then we have the Helmholtz energy with the shortcut A, and this can be described by the function U plus T multiplied by S, temperature multiplied by the entropy. And then we have the Gibbs free energy. The Gibbs free energy is one of the most important values when we are talking about mineralogical thermodynamics. G, we have the Gibbs free energy of a mineral, and we have the Gibbs free energy of the reaction. So in this Gibbs free, this mineral with the lower Gibbs free energy, that is the stable one. So G can then be described by U plus PV minus TS, which is H minus TS. So that means G is for us a fundamental value. The most, and that is because the most important variables in all processes on the Earth are pressure and temperature dependent, as I told you before. And due to the fact that G is a function of pressure and temperature, explains that G is a central key player in mineralogical thermodynamics. So in the relation between G between the chip's free energy, the temperature, and the pressure is following. The chip's free energy is a result of the function of pressure and temperature. So that means G is a state-of-the-art function. The state is defined through external conditions like pressure and temperature of a system, and this system is our planet, yeah, our rocks which we are studying, or our minerals, yeah. And the system is always in a certain state under certain conditions. The mathematical formulation of a certain state is described by the state function. So we have in writing, we have Z, which is the state. We have F, that is the function of the state. So, and then we have the variables of the state, and that is here in this case just ABC, but it is in most cases the temperature and the pressure. So going now to the next slide. Very often while we are doing our calculations, the point of view in a system will change, yeah? So we have Z, which we are using to describe the state, and the state function, or the resulting state function is then an integral function. So, and you know the integral function from school, and now also from the math class at the first year at the university. Then we have the differential function of Z, we are writing dz, that is the change of the state. For example, we are going from standard conditions, and standard condition is room temperature. That means in Kelvin, 298 degree Kelvin and 1 bar, to a certain pressure and temperature conditions of interest. Then we are forming there a differential. So, and that describes then the change of the state and the change of the state function. So we can, for example, writing it as an integral, then we have G is U plus PV minus Ts, where we have now all our variables from the beginning inside. Or we can write it as a differential, then we have dG is du plus pdv plus vdp minus tds minus sdt. And that can be formulated as vdp minus sdt. So and now, due to the fact that dg is a function of the state, which is dependent on the pressure and the temperature, we can write dg as an exact differential function. That means dg is the differential delta g divided by delta t at a constant pressure. That is then, at a constant pressure. And we are writing the differential after dt plus delta g divided by delta p at a constant temperature, and we are writing the differential after p. So, and with this we will then continue tomorrow, and I will just add always slides on this PowerPoint or on this PDF. But I'm just loading it always up that you can follow it every day easily, yeah? Because it depends always how much time I'm having available, because I have 2 classes. Okay, then thank you for listening and see you later.